Applications of inverses. Inverse functions have lots of applications in the real world. Keep in mind, swapping input for output to create a new function insists that we pay attention to the meanings of the input and output variables in the context of any given situation. Inverse scenario 1. Converting dollars to euros. Dollars is input and euros is output. Converting euros to dollars. So we have dollar of x equals 1.18x. Euros is input and dollars is output. Beware, when converting dollars to euros, x is dollars. When converting euros to dollars, x is euros. In other words, x takes on two meanings when considering two functions. Inverse scenario 1. Graphically. Converting dollars to euros, we have euros of x equals x over 1.18, where dollars is input and euros is output. Converting euros to dollars, we have dollars of x equals 1.18x. Euros is input, dollars is output. So here we have, in the black dotted line is our diagonal, y equals x. Here in blue we have our dollar function, and here in red we have our euro function. Inverse scenario 2, converting Fahrenheit to Celsius. C of x equals x minus 32 over 1.8, where degrees F is input x and degrees C is the output. Converting Celsius to Fahrenheit. F of x equals 1.8x plus 32, where degrees C is input x and degrees F is output. Beware, when converting F to C, x is Fahrenheit. When converting C to F, x is Celsius. Be careful, x takes on two meanings. Here we see how converting Fahrenheit to Celsius and back can be represented in a graph. So we have our diagonal here. Here we have our first function that takes Celsius and converts it to Fahrenheit. And here we have our little Celsius machine that you input x and you get Celsius degrees out. Part A. Two children sit on a seesaw. The mass of one child is m1 equals 45 kilograms, and the mass of the second child is unknown. The distances d1 and d2 are measured in meters and give the distance from the fulcrum to each child. The total distance between the children is 5 meters. For a seesaw to be balanced, m1 d1 equals m2 d2. Let d1 equal x and the mass of the second child, m2, be given by f of x. Use the data in the table to write a formula for f of x. Part B, determine the inverse function f to the negative 1 of x. What does the inverse represent in the context of this problem? Alright, so for our part A solution, we have m1 d1 equals m2 d2. m1 is 45, d1 is x, we don't know what that is, m2 is f of x, and d2 equals 5 minus x. So we have f of x equals 45x over 5 minus x. Alright, so now that we have this function right here, we can move on. Part B. Write a formula for inverse function f to the negative 1 of x. What does the inverse represent in the context of this problem? Alright, so now that we have f of x, we can solve for the inverse. So the first step is replacing f of x with y, and on the next slide, we're going to swap x and y. Okay, so we have y equals 45x over 5 minus x. Then we swap x and y, and we get x equals 45y over 5 minus y. So we'll multiply both sides by 5 minus y, and that gives us 5x minus xy equals 45y. Then we're going to rearrange this a bit. We're going to put all the y's on the left side, and then we're going to take out this, we're going to distribute this y out of this. So we have y times 45 plus x over 5x. Therefore, we get y equals 5x over 45 plus x. This is the inverse function. While this function was mass f of x as a function of distance, here we have the distance in meters is a function of mass.